Store implementation is a new object store implementation designed natively for Crimson's threading and callback model. I'm assuming everyone here is at least a little bit familiar with Crimson. So the goal here is to avoid CPU-heavy metadata designs like RocksDB. For context, RocksDB's sort of whole point in life is to spend CPU in order to turn random writes into sequential writes for disks and also flash. This isn't such a good trade-off for the OSD on faster media. And there are other designs that can get some of that behavior without spending quite so much time in garbage collection. But the sort of big concept here is that we want a sufficiently flexible architecture so that we can serve a variety of workloads with different storage configurations. We expect to see a lot of cost-focused capacity workloads using only QLC or ZNS flash devices or hard disks. We also want to be able to serve highly performance-oriented workloads using only fast NVMe devices. And finally, I expect that there will be a lot of demand for a combination of high endurance, low capacity with low endurance, high capacity. So in other words, we'd really like SeaStore to be able to do tiering internally. It would take a lot of pressure off of the design parameters for setting up Ceph clusters, and it would allow people to better combine sort of RGW type capacity pools and RBD type throughput-oriented pools without having to spend, without having to be quite so specific with the cluster setup. So internally to the OSD, there is an interface called the object store. When I say the object store in this talk, that is what I am talking about, not anything else. The object store is the interface by which the OSD talks to its local storage. It has some properties. It is transactional. It is a flat object namespace. Object names may be large because RGW uses them to do direct lookups. So user side S3 names may translate to object store object names within the OSD directly. Each object contains a key to value mapping called the Omap, as well as a data payload. We use that key to value mapping for things like Cephfs directories, RGW, what do you call it, bucket indexes, and certain kinds of RBD metadata. It also needs to support copy and write object clones to support Rados snapshots and therefore Cephfs and RBD snapshots. And we need to be able to support efficient ordered listing of both the OMAP and object namespaces for different reasons. OMAP because it's part of the interface, and the object namespace because it is both scrub and recovery rely on being able to efficiently iterate over the set of objects in the same order on all of the replicas. So at a high level, SeaStore's internal metadata structures look something like this. On the right side of the tree here, we've got the LBA B tree and the backref B trees. These two metadata structures are physically addressed, which means internally each B tree, the internal B tree nodes refer to their children by direct location on disk. And we use these two data structures to maintain an LBA indirection, so that the trees on the left side here, the Onode tree, the Omap B tree, and the actual extents containing object data, do not use physical offsets. They use logical offsets. This is important in SeaStore because it allows us to transparently move around extents, all extents except for the LBA and backref trees, freely without worrying about the data structures they comprise. So the last sort of important bit of journal layout, or a layout for SeaStore, is the way we do journaling. If you're familiar with ye olde file store, or to a lesser extent BlueStore, the journaling mechanism, I believe, is primarily in terms of the user submitted transaction. But with SeaStore, we actually do all consistency at a block level. So SeaStore's consistency semantics are actually totally independent of the object store interface, and they work in terms of blocks. So it starts with a header. We then have a set of deltas, which are semantic changes to a block. And by that I mean blocks are typed, and the deltas have different formats depending on what the type of the block is. So if it's a B tree block, for instance, in the LBA tree or the Omap tree or whatever, the deltas will look like insert key, remove key, that kind of thing. Whereas for data blocks, it'll just be changes to portions of the data range. After that are the newly written logical and physical blocks, and taken as a unit, the entire record represents one unitary change to SeaStore's commit state, including the changes to the LBA tree required to find the new blocks. So the architecture of SeaStore looks something like this. Up at the top, there is the SeaStore class itself, which implements Crimson's version of the object store interface. Below this, we have the Onode manager, the Omap manager, the object data handler, and a few other things responsible for dealing with metadata structures specific to the object store interface. These all deal in terms of logical addresses and are largely oblivious to the underlying storage. Below that, there's a big interface barrier called the transaction manager. This is the layer that handles transactions and extent reads and writes, and is capable of placing extents among different backing devices and doing garbage collection and tiering between them. Below that, we have an extent placement manager responsible for deciding which device an extent actually goes onto, with async cleaner and device implementations for dealing with the actual devices themselves and maintaining free space. And then we have an LBA manager responsible for this physical to logical mapping I described, and a journal responsible for doing transactional consistency. So, without further ado, we'll talk about, my strategy here is going to be to kind of touch on each component, show you the code file responsible for it, and then if anyone has any questions, they can stop me. All right, so the first piece I'm going to touch on is the Onode manager. So this is the metadata structure responsible for mapping a GH object T, which is the OSD's internal type for an object, to an Onode, which because BlueStore used it, it's a perfectly good name for the metadata structure that is the root for a particular object, although other than that, it has no actual relationship to BlueStore's Onode. Similar concept, totally different implementation. So if you're familiar with if you're not familiar with the OSD, a GH object is a tuple with 1, 2, 3, 4, 5, 6, 7 elements to it. The first 3 are fixed size numeric keys, or fixed size numeric values. There's a shard, a pool ID, and the 32-bit crush hash that we get from applying Jenkins, I believe, to the object name. There is a variably sized middle portion, the object name in the namespace. The object name in particular is under the control of the user. And a fixed suffix containing the snapshot and the generation ID. Generation is specific to erasure coding. The order of these elements is unfortunately obligatory because it's how we define ordering. We expect objects listed out of the object store interface to sort with all of the objects in a particular placement group sorted together. So shard, pool, and key have to come first, followed by the object name in the namespace. And then because we want snapshots and generations for a particular object to sort together, those have to come last. So if you've ever designed a B tree with long keys, one really common trick is to elide prefixes and suffixes when they either are prefixes when they're common for an entire node, or suffixes when they are different for every element of a node. And that's what the FL tree implementation does. It takes, as you descend the tree, or at the top of the tree, you primarily store keys containing just the shard, or the shard and the pool and the key. As you get to the middle of the tree, you have to store the actual object name. And then if any particular object has so many snapshots that it fills up a whole leaf node, that leaf node won't need to store the object name because we can elide everything to the left of that portion. So let's see. That code lives the internal to. Can you guys read that at all? How far do I have to?
It's pretty
How
small.
about now? That is that better?
That's legible, yeah.
Okay. So most things in SeaStore have this sort of interface and implementation split, mainly because it makes unit testing easier. So Onode manager.h contains the interface for any implementation of this metadata structure. It has roughly the methods you would expect. You have a way to check for the presence of an Onode. You have a way to get the Onode back. You have a way to get or create an Onode, etc. The actual implementation lives in FL tree onode manager.h. I actually do not remember what FL stands for, but that's the name of the data structure engine invented for this. This code I will not go into in too much detail because it's actually quite interesting. I recommend reading it if you're interested in learning one approach to creating a B tree with this many different possible layouts. But yes, you can find that in staged FL tree in Onode Manager. Let's see. So the next major component up at the top of SeaStore would be the B-tree Omap manager. So I mentioned that every object optionally contains this sort of Omap structure. So the implementation of that in SeaStore is a fairly basic, just string-based B-tree. Because at this time we're not trying that hard to optimize for RGW, not much effort has gone into improving this implementation yet. But eventually we'll probably want to add things like prefix and suffix deletion to this as well. As with the Onode manager, there is an omap manager.h interface file with pretty much what you'd expect. There are ways to list omaps, remove key ranges, clear omaps, etc. With the corresponding implementation, btree omap manager.h. One thing I thought might be interesting here is to show you the this file, omap btree node impl.h, contains the actual extent that we store on disk, or the data structure that represents it. So this is an inner node. So for most of the B trees, there is a type for the inner node and a type for the leaf node. And if I find, hang on. This is a bad example. So this inherits from Omap node, which I believe inherits from cached extent. So many of these things like duplicate for write, maybe get delta buffer. These are methods responsible for hooking into the commit protocol in SeaStore. So when we go to do a commit, we go through every extent and we call these methods on it to prepare it for that process and for putting it into the cache. All right. So the last sort of top level data structure that I'm going to touch on here is the object data handler. Because we have this sparse logical to physical mapping, we don't need to explicitly represent an extent list or anything like that. Instead, what we do is we reserve a large subset of the logical address space and simply let the object use it. Any portions of the space that aren't zero or less than the size of the object get extents mapped to the corresponding logical address. And otherwise, it's simply left unmapped, which represents a missing portion of the object. So we don't need a secondary extent map. That code can be found in objectDataHandler.h, and similar deal. Up at the top here, oh yeah, here's a better example. So struct object data block inherits from logical cached extent, which is the parent structure or the parent interface class for all logically addressed extents. Right. So, I have to actually share the tab. There we go. So now that we've gotten through the sort of top level top level structures. I'm gonna look at read in SeaStore real quick as soon as I can find the tab that has it. One moment. Okay. So I mentioned before that Crimson has its own sort of version of the object store interface, and this is it. It's called Futurized Store because it is basically the object store interface, but interpreted to use Crimson style futures. I'm not going to go into this too much, especially this aerator part, but the gist of it is that read, instead of taking a callback, returns a future object to which you can chain callbacks. So it's sort of a more ergonomic way of dealing with asynchronous I/O. So anything that returns a future is asynchronous. And if you chain a callback onto its return value, it will either execute immediately if the operation is already available, or you will end up returning up to the reactor, and the reactor will run the callback later once the future is available. So these things look synchronous, but they are not. Other than that, the interface looks very much like the object store interface for good reasons. And there's it uses the same transaction structure as Classic. SeaStore's implementation is partitioned so that each SeaStore reactor can get its own local port into SeaStore so that we can avoid synchronization. Other than that, it's a fairly straightforward implementation of that interface in terms of the components I mentioned before. Internally, SeaStore has a transaction structure. Let me find it. That gets passed around to every component that needs to perform reads or mutations. While there are public methods here, users above Transaction Manager don't really interact with them. You use Transaction Manager or other component methods to interact with Transaction instead. And Transaction has two responsibilities. It tracks the set of mutations that the logical commit is trying to perform, so that when we go to do the commit, we can construct the journal record correctly. And secondly, it tracks the read and write sets so that at commit time, we can detect whether a conflicting transaction ended up committing first. This avoids the need to do synchronization while constructing the transaction, but it does mean that it's possible that a transaction will have to be retried if a concurrent transaction turned out to conflict. That state tracking is pretty similar to the state tracking we already need to do for commit, so it doesn't turn out to be a very large extra bit of overhead. Well, let's see if we can find. All right, so here's the read method in SeaStore. So sort of linking together these concepts, we're going to repeat with Onode here is going to pull out from the Onode manager the Onode corresponding to this OID, which got passed in from the user or from the OSD as a GH object T. And then it will call this callback on it with a transaction and the Onode. So we have a check for offset. If it's bigger in size, we just return. But if it's not, we submit the read through to the object data handler, which will pull the metadata that tells it where in the logical address space the data for this object is, and then perform the read. We can then jump over to object data handler to see what that looks like. A little bit more complicated. With object data does kind of the same thing that the with Onode does. It pulls the metadata from the Onode corresponding to this object's data, which contains which contains some information like the whether it has any data at all, and the reserved data base, which would be the logical offset for the 0 offset in the object. After that, it pulls from the transaction manager the set of pins, which would be the set of all mapped extents that fall between the offset and the length of the object. And then it iterates over these extents, ignoring the ones that are 0, and populates the return buffer as needed. Anyone have any questions so far? I know this is sort of a pointillist, I suppose, depiction of SeaStore. I don't know if this is linking up. All right, and we'll move on to the next thing then. So jumping back to Transaction Manager. So the beauty of this abstraction, to the extent that there is one, is that the relatively complex code for especially the Onode tree, but also the Omap tree and the object data doesn't need to worry about the actual location on disks, and it can be entirely agnostic to tiering, garbage collection in general. It also means that we can allow a great deal of transaction concurrency without needing to know ahead of time what will be read or written. So we don't need to make we don't need a sophisticated locking strategy because most of the time we won't have transaction conflicts in the first place. It also means that in the future, if we want to implement metadata structures or pool types that are wildly different from the way Rados works now, we can just add more of these structures on top of the transaction manager and fully leverage all of the lower level garbage collection and tiering. For example, if we wanted to create a data structure dedicated for PG logs, that is a thing we could do relatively easily. Possibly of some interest to Mark. Anyway, so the transaction manager presents a uniform transactional interface for allocating, reading, and mutating logically addressed extents. Mutations to these extents can be expressed as a compact type-dependent delta, which will be included transparently in the commit journal record. For example, the B-tree Omap manager is able to represent the insertion of a key into a block by simply encoding the key and value pair, rather than needing to encode a delta moving all of the subsequent keys one key to the right, which would be much larger potentially. So the code for this is in transactionmanager.h. And the interface looks like a bunch of ways to manipulate logical mappings and to perform reads and writes on extents. So get pins is the method I showed you before, and it simply returns the set of all pinned extents between beginning at offset and extending length. And you'll notice it's a fairly direct call through to the LBA manager. Keeps doing highlighting. Read extent is also probably fairly useful. We call get pin to find the pinned extent at offset. And then we call read pin, which is elsewhere in this file. Hang on. And the code. Yeah, here we go. Yes. Yeah, so the pin has a pointer to the logical extent, which we read here. Sorry, this part's a little bit new. Forgot how that part works. So in general, transaction manager provides this abstraction so that the high-level stuff that deals with Rados-specific data structures doesn't need to know about on-disk allocations, and the stuff that needs to know about on-disk allocations doesn't need to know about Rados. Okay, so for a number of reasons, SeaStore has a cache, both for the usual performance ones, but also for correctness ones. While we have, while there are transactions in progress, the cache represents a projected outcome. So when you go to commit a transaction, the updated versions of those extents go into the cache so that pipeline transactions get the correct versions, especially of metadata structures. So again, this is hidden under the transaction manager, but the code is in cache.h. So this mainly gets access from the transaction manager, but also from all of the other structures under it. It has sort of the usual stuff you'd expect. Cached extent, the parent interface has intrusive members that allow that'll allow relatively memory inexpensive membership in all of the cache internal data structures, including the LRU and other things. There is a basic LRU for managing a configurable amount of memory to be kept around, and some logic for forcing things to remain in cache when they need to be. For instance, the LBA manager has some, or the B-tree implementation at least, has some invariance where it ensures that if an extent is in cache, all of its parents are in cache as well. So we can guarantee that traversing to an extent we already have in cache is always an in-memory operation. So the LBA manager, as I've alluded to several times, is the component responsible for mapping physical addresses to logical addresses. It also includes some other things like reference counts, so that extents that are referenced from multiple places in the LBA tree can be tracked, and we can release them at the correct time. There's also a backref tree implementation that allows us to do garbage collection more efficiently. It's structured very similarly to the LBA tree and uses the same B tree implementation, but the mappings are backwards from physical addresses to logical addresses. And at some point in the future, we will also add the ability to do checksums so that we can get full end-to-end checksumming from the root tree all the way down to the leaves. Should be relatively straightforward in SeaStore since we already do updates that way. See, that code is in this tab. So as usual, there's an LBA manager interface that governs how the rest of the code interacts with this. The interface deals mainly in terms of mappings. So we, for mappings we believe already exist, there are getters. If we need to create a new mapping, there's an alloc concept, etc. And there are ways to increment and decrement ref counts. The only implementation is at this time is the B-tree implementation, which exists in LBA manager / B-tree. The corresponding extent for this is in LBA B-tree node.h, and this actually uses this fixed KV internal node, which is a templated extent implementation that's shared for all of the B trees that use a fixed size int to fixed size int layout kind of mapping. So basically just this in the backref tree. But all of the code responsible for splitting and merging nodes, for instance, is in that template. So some code reuse. Let's see. So the other major component, I think, at the bottom, or one of the other major components at the bottom of SeaStore is the journal, which is responsible for atomically writing and replaying journal records. The interface is in journal.h, which I can find over here. I didn't open this one. Which has operations for submitting a record. This is the primary commit pathway. So you submit a record. Record is a struct containing deltas and extents that the journal then writes down. The commit protocol is actually agnostic as to the final location of the record. The idea being that if we're using a device with anonymous append where you don't know ahead of time what the offset will be, the protocol will still work correctly. Internally to the deltas and records, references to other records within the same record, or to other extents within the same record, are relative to the record base. So anytime you read particularly a metadata extent, you have to adjust the in-memory representations of the child pointers to reflect the actual location of the extent. And then there are methods for replay and for doing commit stuff. There are two implementations of journal. One for segmented devices, which would be devices where we greatly prefer to do sequential writes. That would be ZNS and QLC devices in general, but also some garden variety flash devices as well. And then there is a circular bounded implementation for very fast NVMe devices, which don't have endurance problems when written to randomly. And at the lowest level of SeaStore, most things have worked this way. There's an RBM and a segmented journal. There is an RBM and segmented devices with different update rules, which I'll get to in a moment. So papering over that difference is the extent placement manager. So as I mentioned at the very beginning, part of the core idea with SeaStore is that we want to be able to deal with heterogeneous device configurations. So we wanted to be able to deal with OSD deployments where the combining both fast high endurance devices and slow low endurance devices, which necessarily means that SeaStore needs to be able to manage multiple devices of different performance classes. So the extent placement manager is where all of that business logic lives. It manages placing extents among backing devices, and it has, at the moment, somewhat primitive, but over time, we expect to make a lot of changes here. Heuristics for deciding where an extent should go based on whether it's metadata or a data extent and whether it's marked as cold or hot. And it's also responsible for managing background processes because it is the component that is responsible for knowing what the backing devices actually are. So if you have a segmented device, either as your only device or as a cold tier, then there is a segment cleaner that performs garbage collection on the segments within that device to free them up so that they can be reused. For fast NVMe devices where random writes are efficient, there is an RBM cleaner background process instead. And by background process, I do not mean a separate thread or certainly a separate process. In both of these cases, these are simply callbacks that are called periodically by the reactor. So this is all still local to the same process or to the same reactor thread. And each reactor has its own instances of all of these things. The corresponding code is an extent placement manager.h, which can be found here. So up at the top, there's a bunch of interfaces for exposing writer instances to callers so that we can do things like journaling. And for most of these, you'll notice we have two implementations, a segmented one and an RBM one. The extent placement manager itself, for the external interface that it exposes, deals mainly in terms of allocating extents. And it has a bunch of affordances for the actual commit process. The journal protocol I mentioned before isn't the only way you can write extents. You are allowed to write extents either before or after the commit, but you're allowed to write extents down before the commit, but they will not be linked into the metadata tree until afterwards. And that's this out of line OOL extent concept. So these, like everything else, these things are registered on the transaction, but the extent placement manager is responsible for the for threading those writes through the commit process. Same deal with read. The extent placement manager knows how to translate these p-attrs, which contain a device ID, into the correct device. So first we get the device ID, and then we use the implementation corresponding to that device ID to do the actual read. And then there's some affordances here for doing space management. The extent placement manager is also responsible for tiering. At this time, it's still a bit primitive, but quite a bit of underlying implementation is already present. In that, when there are two devices configured, when they do garbage collection, the extent placement manager is given information about how long ago the extent was written, so that it can make new choices about where to put it. So over time, extents that don't get read or written very often will tend to find themselves demoted to the cold tier. There's work ongoing now to add the ability to do promotion to the hot tier as part of the read path, and a lot of other changes. And as we start getting into more detailed workload analysis, I expect this will change quite a bit.
If I may stop you,
Go ahead.
is it responsible as well for dealing with fragmentation? Do we, and maybe even more important question, are we afraid about fragmentation?
So that is an example of something this component will handle if we decide we care.
I see.
I think we probably do, and we will probably need to make changes to the way the cleaner works so that for instance, when we clean an extent corresponding to an object, we also go and get the other nearby extents and write them all out together. I don't think that work has been done yet, but this is the component it will live in.
I see. We are leaving the doors open.
Yeah. I mean, I expect to need to do that one, especially for hard disks. It's just work that hasn't been done yet.
Yeah, that's actually Spinners was driving supporting Spinners in SeaStore was the driving factor behind the question.
Yeah, we do plan on supporting Spinners, but it's not the immediate goal, like as in the next 3 months. Basically, as soon as someone's willing to start working on it, it'll become more of a priority. It's just a matter of what things are important when. BlueStore is quite good at Spinners, so it's slightly less urgent. But I think long term, we probably do want to have one implementation, but that's very long term. So we'll see. Any other questions on this topic? Right. So, as I mentioned, the segment cleaner is the cleaner responsible for doing garbage collection on segmented devices. This is particularly important compared to with RBM devices because segmented devices have this property that you cannot overwrite written extents. The interface is meant to model the way ZNS devices behave. And if you aren't familiar with those devices, it's an NVMe interface that restricts your access to the disk to appending sequentially to a large gigabytes in size segment, closing it and releasing it. And releasing it releases the entire segment. You're not allowed to overwrite portions of the segment. So for that reason, before you can release and reuse a segment, you need to move any extents that are already there somewhere else. The intention is that if you're familiar with how Flash actually works, internally, there are portions of the device that have to be, that can't be overwritten without zeroing them. So internally, a conventional Flash device does something like this, but exposes to you a mutable interface. The cost is that you have this non-deterministic device-controlled garbage collection process that tends to impact tail latencies. It also tends to produce a lot of extra writes for every write the user does. And that was fairly tolerable for 3-level for TLC devices, but with QLC devices, because the write endurance is so poor, it's important to minimize the amount of write amplification as much as possible. So given that Ceph already needs to do something like tiering, we may as well handle the garbage collection portions as well. Because if we can combine those writes, we potentially significantly cut down on the amount of write amplification, and that should improve device lifetimes. It also means that we get to do the garbage collection stuff when we want to do it, not when the device feels like it. So we have better control over our tail latency. So for these and other reasons, even for non-ZNS devices, we'll probably want to use the segmented interface for slower Flash, even if it happens not to be ZNS. So as I mentioned, it runs within sort of callbacks that are periodically scheduled within the same reactor. Logical extents are simply remapped within the LBA manager. So when we want to move a logical extent around, all we have to do is update in the LBA manager the location of the extent. The conflict detection mechanism will correctly deal with the case where we're relocating an extent that's being accessed by another transaction, because they'll both touch the same LBA B tree extents during the process. So one or the other will retry in the unlikely event that that happens. It's also responsible for throttling foreground work based on the amount of pending garbage collection work. We want to avoid running out of space and having to do a bunch of garbage collection before I/O can resume. So instead, we inject increasingly long pauses as we approach the as the device approaches its sort of hard cap on fullness. I expect that heuristic system will need to change quite a bit, but that is where we are now. Let's see, that code lives in, well, the interface for it lives in async cleaner.h, and I believe segment cleaner is in here as well. Async cleaner is the general interface that the extent placement manager uses to control these sort of background processes. There are a bunch of other interfaces in here also for communicating back to the extent placement manager.
We lost your video for performance issue. Okay, back.
Wait, you guys can see it now? Okay,
Now
cool. Anyway, it's in async cleaner.h. The segment cleaner implementation is in here as well, actually. Yeah, here it is. And you'll notice it inherits from async cleaner and it provides segment provider because it behaves as a it's responsible for mapping which portions of the backing segmented devices are free. And I think that is about all I had prepared. Let me see. Yeah, that's my last slide. Does anyone have any other questions? Yeah, so if you're interested in contributing, we are at a place now where we have sort of fairly basic multi-core support, although Chenmei is working on completing that. And it should be testable if you're willing to tolerate a certain amount of flakiness. We're particularly interested in random write and random read workloads on RBD. If anyone wants to test it and give us feedback. And if you have any ideas for improvements to the various internal metadata structures, we would be interested in that as well, especially if we can identify workloads where it's currently a problem.
Is this already integrated into the Crimson Methodology suite?
I believe it is in the Crimson experimental suite and does not usually pass. The regular Crimson one just runs on BlueStore. Chenmei, you can correct me if I'm wrong, but I think all of the SeaStore tests are still in the Crimson experimental one. That's going to be a priority over the next 6 months, I would say. All right, thanks. I think we can probably wrap it up there. Doesn't sound like there are questions.
All right, thanks a lot, Sam.